Beryl, Beryl, Beryl is my school. Best education reservoir for young learners just like me. Beryl, Beryl.
Okay, hello students. Welcome to physics class. How are you doing? I'm here to get the assignments I gave to you the last time we discussed. And today I want you to look at the board. We didn't exhaust this topic the last time we met, or scalar and vectors. So briefly, I'm going to do a recap of what we did the last time, because we started by defining scalar and vectors. You know what scalar is and what vector is, right? Scalar quantities and vector quantities as well. We have said a scalar quantity is that quantity that has only magnitude but no direction. It has only magnitude but no direction. And then whereas a vector quantity is that quantity that has both magnitude and direction. A vector quantity is that quantity that has both magnitude and direction. We went further to differentiate between a scalar quantity and a vector quantity. We said whereas a scalar quantity has only magnitude and no direction, a vector quantity has both magnitude and direction. We said a scalar quantity is resolved using arithmetic, ordinary addition, whereas vector quantities is using geometric progression. Using geometric progression, we can resolve a vector quantity. Now, in adding a vector quantity, for instance, you can have a force of, let's say, 20 Newton plus another force, let's say, of 30 newtons. If you are to add these two forces together, it will be a force. This can give a force of 30 newtons. Let's say this is 30 newtons, and then plus the force of 20 newtons will give us a force of, isn't it, 50 newtons. This is simple addition. You can see it on the board. The first vector force is 30, the second is 20, and then in addition of two vectors, you have 30 plus 20 will give you a longer vector, which is 50. Is that clear? Okay. And then today we briefly will look at resultant of two vectors. Resultant of two vectors. So if I have vectors just like the one on the board, it could be adjacent to themselves. If you have a vector of this sort and then another of this sort. Let's assume this is 20 Newton, this is 30 Newton. Now these are two vectors acting perpendicular to each other. They are acting perpendicular. That is, they're making an angle 90. Okay, how do you resolve it? The third vector is also a single vector that have the same property. Of both the first and the second vector. So this is arrow. Isn't it? So finding this arrow, last time I told you we can use Pythagoras theorem. In finding it, we can use Socratoire, which is also embedded into Pythagoras theorem. We can use the cosine rule or the sine rule as well, but you must know how to apply them. Don't forget, in representative vector, I told you last week that you must be able to draw the compass, right? To define the direction of vectors. This is the north pole, this is the south pole, this is the east, and this is the west. So you can represent any vector, maybe southwest, you see it? Southwest, or northeast, Now these are the various ways you represent vectors. Either southwest, northeast, northwest, and so on and so forth. Or that is, this is northwest, this is southeast. Is that clear? These are how you can represent vectors. But today we're going to deal on how to resolve, or we call it resultant of two vectors. Resultant of two vectors. Now, resultant of two vectors. We said the resultant of vectors is that single vectors which would have the same effect in magnitude and direction as the original vectors acting together. Now, there are in general two methods of adding or compounding vectors to find the resultant. What this simply means is that when we say there are two vectors, like what I showed you earlier on, and if you have a vector of this sort, let's say this is 30 Newton, and then another vector, 20 Newton, I said they must have the same origin. This is 20 Newtons, right? These vectors are to be resolved. And if they are to be resolved, we said there are two methods that are involved. The first method is the parallelogram method, which you can call it the parallelogram law of vector. And then the second method is the triangular method, or you call it polygon method. If you don't call it the polygon method, you can also describe it as a triangle method. But there is a slight difference between the triangular method of resolving the vector compared to the polygon method, just depending on their shapes. Is that clear? Okay. Now these vectors are to be resolved. If they are to be resolved, we have a single vector, that what we said there, that is the same in its magnitude and direction. And this, a vector can come from this. Sorry, my line may not be very straight. Pardon me. Okay. Now we can name this vector R. We can name this vector arrow. But that's different from when we are employing the first method. The first method in resolving two or more vectors. We said the parallelogram method is inclined to each other. That's the resultant of two vectors inclined to each other may be represented by the diagonal of a parallelogram. May be represented by the diagonal of a parallelogram drawn with the two vectors at adjacent sides. In this method, the two vectors are drawn from a common origin. I have explained that, what a common origin means. And a parallelogram is constructed using these two vectors as adjacent sides. The resultant is the diagonal drawn from the common origin. Let's have a trace of a vector. Now you have, sorry for that, let me use this other marker. Okay. That's a vector, let's say 3 units. Then you have another vector. Let's say this is 4 units. This is 4 units. Now if we have to resolve this vector, let's trace it this way. Let's say have this. Maybe this is A, this is B, this is, I say this is D. Trace it this way. Trace it this way. You can have A, B. Let's say this is C, and this is D. Okay. Now, how do you resolve a vector using parallelogram law? Is what I'm trying to show you. Now, with this, we can take a diagonal. I draw the diagonal of this vector to this point. There's an angle sustained here. There's also an angle here. There's an angle here. Now, if you look at this vector, you discover that this is as this is 45 degrees, this is theta. Now if we have that way 45 degrees, this is 180 minus 45 degrees. Isn't it? Okay. So when this happens, this is a typical shape of a parallelogram. A typical shape of a parallelogram, and once this is done, we can now start to resolve the vectors using the law of a parallelogram of vector. The law of a parallelogram law of vector. Okay, now if you look at this sketch on the board, the shape of a parallelogram. First of all, this is point A, this is B. So we'll take this to be vector U and vector V. Isn't it? This is a vector, this is also a vector. Now from this vector, they have their common origin from that point. So we had to sketch this. This is like a mirror image of this. So you have V here. The length from A to D is the same thing as the length from B to C, right? And the length AB is the same thing as the length DC. You see, for a vector. Now, to resolve this vector, we said the law of parallelogram is applied. And the parallelogram law of vector states that, is on the board, two vectors are represented in magnitude, and that is, if two vectors are represented in magnitude and direction by the adjacent sides of a parallelogram, the diagonal of the parallelogram drawn from the points of intersection of the vectors represents the resultant vector in magnitude and direction. This is exactly what we are talking about. From point A to point C, you have the resultant vector. Now, if we are to resolve this vector, we are going to apply the cosine rule. The cosine rule, remember I told you about the Pythagoras theorem the last time. So let's resolve this. Now, if we are resolving R, which is AC, that is AC squared, using the Pythagoras theorem, is equals to this, which is AB, is equals to AB squared plus AD squared. You see it? AD squared plus 2 into AB times AD cos 180 minus, excuse me, cos 180 minus theta. This is theta, and this is the angle we are looking at. Now we can resolve this until we are able to get AC, which automatically becomes the resultant vector for this parallelogram. Do you get it? Do I go through it again? Okay. Using Pythagoras theorem, I said we can resolve this vector or vectors. Don't mind you, we have two vectors here. Okay. From this diagram, we have that AC, which is the resultant vector from this point to this point, is AC. That's where you have AC is equals to AB squared. AB squared plus AD squared plus 2 of AB and AD cos 180 minus theta. Cos 180 minus theta. So if you look at the parallelogram flow of vector, we can go over it again. It states that if two vectors are represented in magnitude and direction by the adjacent sides of a parallelogram, the diagonal of the parallelogram drawn from the point of intersection of the vectors represents the resultant vector in magnitude and direction. Now we're going to apply this. Looking at it, it looks as if you're getting confused. When we apply it on a particular maybe question, it becomes very clear, right? Can we apply it? Let's apply it. Okay, let's apply it using this example. Now, on the board you have example 1. Find the resultant of two vectors of 3 units and 4 units acting at a point O at an angle of 45 degrees with each other. Now, the first thing you do is to try to do a sketch of the vector. And you don't just try sketching a vector without first of bringing out your scale rule. You first of all have a scale, and I said by scale drawing, choose a suitable scale and draw the vectors OA and OB to represent 3 units and 4 units at an angle of 45 degrees with each other. This is the first step. You have to bring out, choose your scale. After choosing the scale, represent it just like I have here. Draw the vector OA, you have OA and then OB to represent 3 units and 4 units and at an angle. You see the angle there, 45 degrees with each other. So from these two vectors, I can now highlight this, trace it to bring out a parallelogram. Now from the parallelogram, I will trace the diagonal which is OC. Now it's the diagonal that will form the resultant of this vector arrow. It's the diagonal. So using analytical method, we can obtain the resultant vector by cosine rule. Of course, you know how to bring out your cosine rule from a diagram of this sort. So the resultant, which is arrow, is OC. So I will have OC squared is equals to OA squared plus OB squared. Are you following? Plus 2 into OA times OB. Isn't it? Into OA times OB, right? Cos 180 minus, I'll break that down. Okay, from here you have times OB cos 180 degrees minus, now what is this angle here? If you take away, this is sustaining an angle 180. I got a straight line is one. Take away 45 from this, you have 135 degrees. 135 degrees. Now from this point, it becomes very easy to resolve OC, which automatically becomes the resultant of this vector. Shall we? Okay. From there you have, what's OC? OA is 3 squared plus OB is 4 squared plus 2 into 3 times 4 cos 45 degrees. Take away 180 minus 135 from 180, you have 45 degrees. So this is 3 squared is 9 plus 16 plus 2 into 3 times 4 is 12 cos 45 degree, and that's 9 plus 16 plus 2 times 12 is what? 24 cos